We talked last week about some of the characteristics of quadratic equations and the graph that those quadratics will make, which is called a parabola. So we're going to look at some applications of quadratics and how those characteristics are reflected in real life applications. So our first one, I'm looking at the notes for applications of quadratics, and our first one says a water balloon is catapulted in the air so that its height h in meters after t seconds is h equals negative 4.9 t squared plus 27t plus 2.4. You'll notice that the negative 4.9 is in meters, and this is actually the acceleration of gravity. So what we're going to look at is a graph. I have already gone into Desmos and added the graphs of these pretty much through all the whole worksheet so that we can really just focus on the characteristics of the graph and how that applies to the word problems. So the first question is, how high is the balloon after 1 second? Now, 1 second is going to be the t value, which is the input in the problem, or the x value if you're thinking about the graph. So I marked here where we are at 1 second. That's what this orange dotted line is. And you can see that it touches the curve at this point, and that is 24.5 meters high. So the balloon is 24.5 meters high after 1 second. The second question, for how long is the balloon more than 30 meters high? Okay, so on the graph, 30 meters is right here, and the amount of time that it is above that line is going to be from here to here. So we look at the time here and the time here, and then we can subtract. So we have 4.154 minus 1.356, and then we just do the subtraction. So just under 3 seconds. So this is 2.798 seconds, I believe, yes. And then part C, what's the maximum height? Well, if you just visualize what's happening here, you can see that the maximum occurs at the vertex, which is what we talked about last week in our booklet. The maximum always occurs at the vertex, and we're asking what is the actual height of the balloon at that point, and height is the y value, so 39.594 meters would be the maximum height. And then the last question, when will the balloon burst as it hits the ground? Okay, well, the ground is at height 0, so that's going to be either here or here. Well, obviously we don't want time to be negative, so we're going to get rid of that one. So the other one would be 5.598 seconds. The balloon hits the ground at 5.598 seconds. Next page, quadratic word problems. A fireworks rocket is launched from a hill above a lake. The rocket will fall into the lake after exploding at its maximum height. The rocket's height above the surface of the lake is given by that function g. What's the maximum height of the rocket? Well, you can kind of visualize what's happening with the rocket up here, and we are told that it's going to explode after it hits its maximum height, and there's the maximum right there at the vertex. The maximum height is the y value, so that would be 144 feet. The x value at that point is the time that it is in the air. So 2 seconds is how long it takes to get up there, but the maximum height is 144 feet. The next one, a fireworks rocket is launched from a hill above a lake. Same idea, same graph in fact. How long will it take the rocket to hit the lake? Okay, so the lake is at height 0. So we're going to hit the lake right here. This is where it hits the lake. And so we can see the amount of time that it takes for it to be at height 0 is 5 seconds. Next, we're going to look at a rock thrown from the top of a tall building. The distance in feet between the rock and the ground, x seconds after it's thrown, is given by this function, f. How long after the rock is thrown is it 340 feet above the ground? So I went ahead and graphed both the function and the height, 340 feet. Now we don't even have to worry about this side of the function because time is not going to be negative. So we're really just focusing on this side. And we want to know when the height reaches right at 340. And so I found the intersection of those two graphs, and we get 1.5 seconds. Then we have, again, the same graph. This time we want to know how long after the rock is thrown does it hit the ground. Okay, so we are looking for a height of 0 if it hits the ground, right there. And it looks like 4.763 seconds. 4.763 seconds. The closest one I have here is 4.7324. Okay. Next one, we have a superhero wanting to leap over a building. They're gonna, so he can take a shortcut down the alley. There's the function and its graph. The building is 420 feet high. So how high can the superhero get? At his maximum, he can only get about 352 feet. Is he going to clear the building? No. He will crash into the building at about 351 feet because he can't quite go high enough. Bummer. Number 6, the height in feet of the curved arch support for a bridge can be modeled by this function. You're standing on a platform 2 feet above the maximum height of the arch. If you bungee from this point and your bungee will stretch 420 feet before retracting, are you safe? So you're going to stand 2 feet above the maximum height. Well, the maximum height is about 429. So you're standing at about 431. Now, if your bungee stretches 420 feet down, will you hit the ground? Well, if you go 420 feet down, you should still end up with 11 feet to go. So yeah, you're safe. I don't know about totally safe. I would be a little freaked out, but I think as far as the math goes, you're safe. Number 7, you're interested in retrieving a souvenir from a shipwreck that's located 115 feet below the water. You don't have any diving equipment, so your dive is limited by that equation that's listed there. Assuming you could hold your breath for the duration of the dive, would you be able to retrieve your souvenir? So how low does this graph go? All right, so the x-axis is the water level, and you can go this low. Be underwater 118 feet. Is that going to be far enough? Yes, it is far enough. You will be able to reach the souvenir. Now, what about holding your breath? How long do you have to hold your breath until you resurface? Okay, well, you're going to start and you're holding your breath. I guess you start underwater. Interesting. But you're going to be underwater all this time, and you're going to finally hit the surface again at about 89 seconds. So how long do you have to hold your breath? Almost 90 seconds. So this lesson is really about looking at the graph and understanding what the input, the x values represent, what the y values represent, and especially what the vertex represents. On the next page, Jason jumped off of a cliff into the ocean in Acapulco while vacationing with some friends. His height is modeled by that function, where t is the time in seconds and h is the height in feet. So the first question, how long did it take for Jason to reach his maximum height? All right, so he was already on top of a cliff. That's why we're starting right up here. He's already up on top of the cliff, and he jumps and then falls to the water. So how long did it take him to get to his maximum height? Well, the maximum always occurs at the vertex. So that's going to be half a second, 0.5 seconds to reach the maximum height. And how high was that point? How high did he reach when he jumped out into the ocean? Well, the height would be 484 feet. What was his initial height? Well, I didn't click on that intercept, but one thing that's handy, remember, about standard form is that the y-intercept, where he would have jumped right off of the cliff, is the constant. Remember that? 480 was the height of the cliff. So this is where it's tying into what we did with those booklets before. We talked about vertex form mostly to start with, but we did connect the fact that the y-intercept, which you see here in the graph, the y-intercept is the same as the constant in the standard form. Always, it's the same as the constant. So you can find it by looking at the standard form. The c value at the end tells you the y-intercept. Number 2, if a toy rocket is launched vertically upward from ground level with an initial velocity of 128 feet per second, notice that 128 is right there, negative 16 is the acceleration due to gravity measured in feet per second, then the height is given by this equation, and we're ignoring air resistance. So how long does it take for the rocket to reach its maximum height? Well, again, maximum and minimum, those always occur right at the vertex. So the amount of time, 4 seconds. The maximum height itself, well, how high does it get at that vertex? 256 feet. And then how long does it take to reach the ground? Okay, well, if it's reaching the ground, it's going to have a height of 0. So how many seconds did it take? 8 seconds to reach the ground. Number 3, you're trying to dunk a basketball. You need to jump 2.5 feet into the air to dunk the ball. The height that your feet are above the ground is given by this function. What's the maximum height your feet will be above the ground? And will you be able to dunk it? Okay, so this graph shows the height that your feet are above the ground when you jump. So let's see, how high can you jump? At the highest, at your peak, you are 2.25 feet off the ground. Are you going to be able to dunk the ball? Not quite. 2.5 feet would be up a little bit higher. Your feet need to be all the way up here at 2.5, but they're not quite high enough. So what is the maximum height your feet will be? 2.25 feet. And how high will you be able to dunk the baseball or the basketball? Nope, unfortunately not. Number 4, a ball is thrown in the air. The path of the ball represented by the equation h of t, etc. Graph the equation, I already did that for you, over the interval from 0 to 8. So you see 0 is when it's being thrown into the air, and 8 is when it's coming back down. Graph it on that interval. What's the maximum height? Okay, well, the maximum again occurs at the vertex. So the maximum height would be 16 feet. I believe it's feet. How long is, oh, no it isn't, it's meters. How long is the ball above 7 meters? Well, let's see. We would need to find where the graph intersects 7 meters. So I'm going to show you how I do that. I'm going to open Desmos here, and we're going to graph the function. I'm just going to use x and y. So y equals negative x squared plus 8x. And I'm also going to graph y equals 7. So you can see the colors are a little different, but you can see it's the same graph. Now I'm going to just touch the graph here on Desmos, and notice that it highlights the graph that I touched, and then I'm going to touch the intersection points, and you can see there that we have an intersection point at 1, 7 and another one at 7, 7. So this is 1, 7 and this one is 7, 7. So the question again asked us, how long is the ball above 7 meters? So from this point to this point, how much time passes? From 1 until 7 seconds, that would be 6 seconds passing. 6 seconds. And then to rewrite the equation in vertex form, we're going to put the vertex, see it's x minus 4 and squared, and then plus 16. Because remember we have x minus the number, that's our transformation to the right, 4, and then plus a number on the end, that's transformed up 16. Now the fact that it's upside down, it's reflected down, so we need a negative out in front. So the vertex form of this equation is h of t equals negative of x minus 4 quantity squared. Oops, I'm sorry, make that a t since we've got a function in t. T minus 4 quantity squared plus 16. There would be our vertex form. Number 7. The following equation represents the path of a donut hole being thrown by Mr. London, where x represents the time in seconds the donut's in the air, and y represents the height in feet of the donut. All right, I went ahead and graphed it for you, and there's 3 points shown. So the question, at what time does the donut reach its maximum height? And again, maximum height occurs at the vertex. So this is going to be 2 seconds and 2 feet. So what time? 2 seconds. And what is the height? 2 feet. Writing the equation in vertex form, we're going to have the vertex, let's see, it's moved to the right 2, so that's x minus 2. And then it's moved, let's see, up 2, so plus 2 at the end. And it's also flipped upside down, so we need a negative in the front. And we used just a y for the front. So there's our vertex form. A small independent motion picture company determines the profit for producing a certain number of DVD copies and of a recent release is this function here. And the profit is in thousands of dollars, and in is in thousands of units. Okay, so how many DVDs should the company produce to maximize their profit? Okay, so maximum occurs at the vertex. So the number of DVDs, remember, N is the number of units itself. So the number of DVDs is 85. So that's, or it's actually in thousands, so 85,000 DVDs. And then the maximum profit is the Y value, because P is the output. That's the Y values here. 128.5 thousand, because this is in thousands of dollars. That's going to be their maximum profit and how many DVDs they should sell to reach that maximum profit. Okay, next we're going to look at a couple of graphs, and we just want to write the equation in vertex form. So you'll see that the vertex here is -2, -3. So that is to the left 2, so that's x plus 2 for transformation purposes, and then -3 because it's shifted down 3. And notice that instead of when we square 1, we moved up, we usually move up 1. This time we're moving up 2 spaces. So that's a vertical stretch by a factor of 2. You can also look at, if you go another, 2 squared is normally 1, 2, 3, 4 spaces, but this is 5, 6, 7, 8 spaces. So that's twice as many as we would have anticipated without the stretch. So we can always double check by using Desmos to graph and see if our equation matches up, makes our graph match up. So we're going to type in y equals 2 times x plus 2 quantity squared minus 3. How's that look? Is the vertex the right spot? -2, -3. And do we have a point at, let's see if the point -4, +5 shows up right on our graph like we hope it should. It sure does. So that ordered pair is on the right spot, and it looks like the graph that's given has a y-intercept of 5, and so does ours. So we've got the correct graph and the correct equation for this graph. Now the other one we have over here, our vertex is at 4, 1. So our transformation, we moved it to the right 4, so that's x minus 4, quantity squared, and up 1, so plus 1 at the end. Now this one is going to go down, and it's kind of stretched, or is it compressed? It's a little hard to tell. So what we're going to do, we're going to put y equals, and I'm just going to put an a here. It's the same a as if we would have had ax squared plus bx plus c in the standard form. It's the same a. We're just going to use it in a slightly different way. So I'm actually going to plug in this x, no, not this one, this x and y into this equation and figure out what a would have to be. So let's plug in the 1 for the y. I'll leave a as a variable and plug in 4. Nope, not 4. Where was I going with this? Let me try that again. Not 1. We want to plug in 7, -2. That's better. Okay. So we plug in -2 for the y and 7 for the x. There we go. And now we're going to solve for a. So we have 7 minus 4 is 3. We square it and we get 9. So that means we have 9a. So 9 times a is 9a plus 1 equals -2. And then we need to subtract the 1. I'm going to move all of this over to the side so we have a little more space to work. We're going to subtract the 1 from both sides. So that gives me -3 equals 9a. And then I'm going to divide everything by 9. Which, if you notice, both the numerator and denominator are divisible by 3. So that simplifies down to -1/3. There we go. So now to rewrite this all in vertex form, we have y equals -1/3, we just figured out, and then multiplied by x minus 4 quantity squared plus 1. We could have done the same process to solve for a on the previous problem. I'll show you why that works, or show you how it works. So let's say we didn't know that this was going to be 2. We could take and plug in a here and use this ordered pair that's over here, -4, 5, and plug those in for the x and y to see just what happens. So 5 equals some a value we don't know, and then -4 plus 2 quantity squared minus 3. So we get -2 when you square it. That makes +4. So this is +4 times a, 4a minus 3. And then we're going to add 3 to both sides. So we get 8 equals 4a. And then you need to divide by 4. And voila, we get a equals 2, which is what we had before. I just wanted to show you that that process works, even if you don't happen to notice, oh yes, 1 over and 2 up would be a point. 2 squared normally is 4, but this time it's 8. So either way works. Y equals 2 times x plus 2 quantity squared minus 3. All right, moving on. Courtney is building a rectangular wading pool. She wants the area of the bottom to be 54 feet squared. She also wants the length of the pool to be 3 feet longer than twice the width. What are the dimensions of the pool? Okay, so I went ahead and wrote the function for you. To find the dimensions of the pool, you want to have the area to match up. So we want to make this equal 0. So it's going to be right here. So 4.5 is what is going to be the width. Notice that we can't have a negative width, so we just ignore the negative 6. So our width is going to be 4.5, x equals 4.5. And then we know that the length is 3 longer than twice the width. So we double this, which would be 9, and add 3, and you get 12. So we have 4.5 and 12 feet. Those are your dimensions. So this time, instead of using the maximum or minimum, in this case it would have been a minimum, we actually used an intercept. So one of those other characteristics that we marked in our little booklets. B, the formula for throwing a basketball in the air is represented by that function h. H is the height. So after how many seconds will the ball hit the ground? Okay, so we're starting at time 0 right here, and then we're throwing it up into the air, and then it falls down and hits the ground at height 0. So height 0 happens at 2 seconds. C. The function h gives an object's height in feet at t seconds. And here is that graph for you. What does the constant tell you about the height of the object? Okay, remember, here's our constant. Here's our constant. And if you look at your graph, where does 1700 show up? Right there, the y-intercept. So, since it's the y-intercept, that means time is 0. So that is at the very beginning, before it is thrown into the air or before it falls from whatever height. So this is its initial height, the start. The constant tells you the initial height. That kind of is the same thing over here. When you start with throwing a baseball, the initial height was 40. I'm not really sure why you were throwing the baseball from 40 feet up in the air, but that's the idea. It started at 40 feet. We can look at that in several of the other examples. The initial, let's see, where's another one? Here we go. Let's see, right here. So on this one, the ball is thrown in the air, and the initial height right here was 0, 0, at that 0, 0 point. So the initial height was at 0, so they threw it from the ground for some reason. You're trying to dunk a basketball, your feet initially are at height 0 on the ground, which makes sense. Okay, so back to where we were. The constant tells you the initial height, and remember this is in standard forms, but the constant will do that. Part 2, what does the coefficient tell you about the direction the object is moving? Well, if we have a negative 16, then we know that the graph is flipped downward, and so the object is going to move down. It's going to be falling. The direction the object is moving is down. A negative coefficient makes the graph, tells you the object is moving down or falling. Part 3, when will the object be 1,000 feet above the ground? Okay, well, I went ahead and I graphed 1,000 feet, and we can see that the projectile graph and the 1,000 feet graph intersect at about 6.6 seconds. 6.614 seconds. what are the reasonable domain and range? Well, we're talking about time for our domain. So 0 is the smallest we can go, and the highest you would want to go, well, I would probably stop right here, because once the object hits the ground, it's not going to be moving any further. I mean, we assume. So I would say the domain would be from 0 to 10.308. And the range, well, the highest this graph goes, and you have to keep in mind that time being negative doesn't make any sense, so really that part of the graph isn't even applicable. So the highest the graph goes would be 1700, and the lowest the graph goes was 0. So from 0 to 1700 would be a reasonable range for this graph. All right, now we have a few more. The next one, and notice that I still have given you all of the graphs here. Here's one here. Let's jump down to this one. A rectangular field will be fenced on all 4 sides. There will also be a line of fence across the field parallel to the shorter side. I've given you the diagram already. I wrote the equations. I even gave you the graph. So if 900 meters of fencing are available, what dimensions of the field will produce a maximum area? Okay, so maximum is the key word there. Maximum always occurs at the vertex. Here's the vertex. What are the dimensions? Well, x is 150. And so we have 150 on this side. And if I plug in 150 over here, 3/2 times 150 would be, let's just calculate it, I guess. See, 450 minus 3/2 times 150. Okay, 225. So the other side would be 225. Okay, and that's really all that you needed to know. The dimensions, well, let's see, y would equal 225. So those are the dimensions that produce the maximum area. And what is that maximum area? Well, looks like 33,750 square feet are going to be your maximum area. Oh, I'm sorry, it's meters, square meters. So here is the maximum area that you can get for your garden. All right, here's another one. This one's pretty interesting, I think. Tickets to a school dance cost $4, and the projected attendance is 300 people. For every 10-cent increase in ticket price, that's what I'm showing here, increasing from $4 up 10 cents each time, the dance committee projects that attendance decreases by 5. So normally there'd be 300, but every time they increase the cost, 5 people decide, I'll do something else. So we want to maximize the revenue, and you make money by charging a certain amount and having people buy those tickets. So you multiply the number of tickets times the price of each one. And so here's a graph of that situation. And you can see that our maximum or greatest possible revenue, again, always occurs at the vertex, is going to occur when we increase 10 times. So if I increase 10 times, how much money am I actually charging? Well, let's see, the ticket price that will produce the greatest revenue, I'm starting with $4 and I'm increasing 10 cents 10 times. 10 times 10 would be $1. 4 plus 1, $5 would be the greatest revenue, or would be the price of the tickets that would give me the greatest revenue. And that revenue would be $1,250. So the maximum occurs at the vertex, or the minimum if you are looking at a parabola that opens up. And I believe that would be the end of the notes. So I've left just a couple here for you to do on your own, and I would like you to do those, answer those questions, and then when you're done, I want you to take a screenshot of just this just these examples right here. Take a shot of it, and upload it into Google Classroom in this folder.